So I'll go ahead and do the factoring and the math knowledge question and pause the video, and then once everyone is finished, I'll go over how to do them. So this is a squared x here, and an x if you need help thinking about how to do those. You would say 2, and then x, and then 2, and we're going to do a minus 3, and then a plus 4, and then if you reduce it, you would have 2x minus 3, and then x plus 2, but it's not really a squared, it's to the 4th, so we make these squared, and then neither one of those will reduce, so this would be your answer there. Looking at the math knowledge question, she read a 12th of the book for the first 3 days, so a 12th each day would mean she has finished a 4th of the book. So she has 3/4 of the book left, and she needs to do it over 5 days. So divide it by 5, or 3/4 times 1/5 would give you 3/20, which is D here. So that would be your answer for those two. All right, so we're looking at lesson 75 today, continuity of functions. So hopefully after this lesson you'll understand continuity of functions. We're going to start off with the intermediate value theorem. If f is continuous on the closed interval from a to b, and n is a number between f of a and f of b, then there is at least one number c between a and b, inclusive, for which f of c equals n. So you have to have a continuous function here. It has to tell you that it is continuous. If it doesn't say continuous, then you won't be able to use this. It must tell you that the function is continuous. And I'm going to show you a little picture here. We have a continuous function from a to b. And if you look, this is our a, 2. And so whatever this is f of 2. And then 8 is our b. And so this value here is f of b. Because if you just kind of draw it over, that's about what it would be. So if c is in between a and b, I'm going to put c right here. We wanted to get to a 42 because that's what they gave us here. And there is some number c. We don't know where it is. I obviously didn't draw it exactly correctly, but it's over here. And there is some number on that function that when I plug it in, I'm going to get a 42. Now, it doesn't tell you what the c value is. It just tells you that it exists. Okay, so that's the intermediate value theorem. That if you're going from here somewhere over to here, then in between those, we had to have hit that value, whatever it is that we are looking for. For this one, it's 42. So if we started here at 2, and then we went up to 50 over here for our y values, then some point in between those two, we must have hit every number between 2 and 50. And so that's what it's saying. So we want to prove here that it has a root between 0 and 1. So first off, we must know that it is a continuous function. This is a continuous function because it's a cubic. It's a polynomial function, and it is always going to be continuous. So we need to figure out what is f of 0. Well, if you plug in 0, you get that f of 0 equals 2. We also need to figure out what f of 1 equals. So if you plug in 1, you end up getting -2. And so it wants us to use the intermediate value theorem to prove that there's a root between 0 and 1. Well, if I sketch this out, when I plugged in 0, I got 2. And when I plugged in 1, I got -2. Well, if this is a continuous function, it has to go from one point to the other. And so at some point, it crosses the x-axis. And that is what a root is, where it crosses the x-axis. So because this y value is positive and this y value is negative, that means that we have to have a root in between there. Now, we don't know what the root is. We could use our calculator if we really wanted to find it, but we just know that it does exist. And all it said was prove that it has a root. It didn't say prove or find what that root actually is. Okay? So we proved that it has a root because this one here is positive and this one here is negative. So at some point it had to equal 0, going from a positive number to a negative number. Okay? So now look in here. Which of these is a continuous function on the interval from a to b? Now notice, this is an open interval because we've got parentheses. So we don't need to have closed circles at the end. Well, this first one is not continuous because we have a jump right there. This one down at the bottom is not continuous because we've got a hole. But this one is continuous. There's no jump, there's no hole. We start at A and we end at B. Okay? Looking at definition of continuity at a point. A function f is continuous at a point C if f exists at C and the limit as x approaches C, there's a little minus sign here, from the left of your function equals the limit as x approaches C from the right, if that also equals f of C. So it says a function is continuous at the point C if f exists at C and the limit from the left and the right are also the same as the actual function. So let's draw a picture here. If I have something like this, the left and the right hand limits are the same because it's approaching a hole. However, the function value is actually whatever that point is. So while the left and the right hand limits equal each other on this graph, since this picture shows a hole with a little dot below it, those three values are not the same. So this would not be a continuous function. But looking here, if I have a function like that, and I'm looking at this point, the left and the right hand limits are the same, and whenever I plug in the number, I get the same thing from this point. And so that would show you an example of a continuous function. Now looking at the definition of an open interval continuity. If you have your function f is continuous on an open interval from a to b, that means that it is continuous at every point on the interval. So it's not looking at the endpoints at a and b, it's looking at every point in between those two on that interval. Okay. Now looking at the definition of closed interval continuity. So a function is continuous on your closed interval from a to b if it's continuous at every point between a and b, and if it is defined at both a and b, and also if the limit as x approaches a from the right equals your f of a, and the limit as x approaches b from the left is equal to f of b. So if I draw a function and it's going to be closed, so we're coming from the right here. This is my a value, and that's my b value. And so the limit of the function as I approach a from the right has to equal whatever the f of a is. And then for the other one, as you approach it from the left, it has to equal whatever this b, f of b value is. So the closed interval continuity has to have a little bit more information for your endpoints to know that it is actually continuous. All right, so let's look at this example. Suppose the function f is defined on the interval from 1 to 3. And then it tells us that f of 1 equals 1 and f of 3 equals 7. And does a number c exist in between 1 and 3 such that f of c equals 3? Now you may think, okay, well if I graph it, 1, 1 was a point, and then 3, 7 was a point. And if I connect those, at some point I'm going to have to hit that 3. And it's going to happen right there, whatever that number is. However, did it ever say in the problem that we had a continuous function? No, it doesn't. So, does a number c exist? And the answer would be not necessarily. It's not a yes it does or a no it doesn't. It's not necessarily. And it's because they don't tell us that the function is continuous. However, if the function were continuous, then the number would exist. But since we don't know if it's continuous or not, we don't know for sure whether the c exists or not. So our answer is just not necessarily. Okay? Looking at the next example, suppose f is a function that is continuous on the closed interval from 1 to 3. Which of the following could be the graph of f? Well, it did tell us it's continuous. All of these are continuous. Now it said a closed interval. Well, A has open ends, so it's not closed. Same thing for B. Open ends, it's not closed. For C, we've got an open end here. It's not a closed interval. However, for D, we have colored in circles there. That means it is a closed interval. So D would be the only option for the continuous function on the closed interval 1 to 3. Okay, now let's look at the next example. F is a piecewise function defined as follows. The absolute value of x plus 3 whenever x is less than 1, and then ax squared plus bx when x is greater than or equal to 1. We want to find the values of a and b such that f is continuous on our interval from negative infinity to infinity. Now, I really like these. I think they're kind of fun to try and figure out. I always like to start with a graph on these. And so the first one is the graph of an absolute value. And so this is an absolute value pushed up to 3. So I'm going to start off by graphing the whole thing, and then I'm going to erase part of it for you. And so that would be an absolute value plus 3. But it's only when x is less than 1. So I'm going to put x equals 1 right there. And so then we would have it like that. And now it is a open circle because it was just less than 1. It's not or equal to 1. Now looking at this next part, ax squared plus bx. That's the graph of a parabola. All we know is that it's a parabola, and it's only whenever x is greater than or equal to 1. Now, I don't know if it opens up or down because I don't know what the value of a is. So I'm going to have some parabola here, and it's going to be opening up. And we need it to be continuous functions. We have to have a continuous function here because it says such that it makes it continuous. So that means that that little dot right here needs to go right on top of the open circle that I have there. So we don't know exactly where it is. We just know that that little open circle needs to be covered by the dot that I drew. Now it could be flipped and go down. We don't know. That's what we got to figure out. And so the way that you're going to do that, we need to know when does the absolute value of x plus 3 equal ax squared plus bx. We need to set those equal to each other because we need them to intersect at this point right here. Now what x value is for that point? Well, when x equals 1 is what we're dealing with. So we're going to plug in a 1 here everywhere for our x. And so if you simplify this, that's the value of 1 is 1 plus 3, 4. And then we have a times 1 squared is still a, plus b times 1, which is b. And I get the equation a plus b equals 4. I don't have any other information other than that. And so you can pick any value for a and b as long as they add up to 4. So any number that you want, as long as they add up to 4, that would work. So you could say a equals 2, b equals 2. You could say that a equals 2 million. And then you would find your b would have to be negative so that they add up to 4. But really, you just need two numbers that add up to 4. And so usually I think they put that for the actual answer. A plus b has to equal 4. Okay? So that's how those work. Again, I think they're kind of fun because you're kind of manipulating a graph. But they're not too bad. You basically just set the two function piecewise parts equal to each other and plug in the x value. So let's look at this one. We have a piecewise function where x squared minus c squared over x plus c whenever x is not equal to negative c. And then we also have 2c when x is equal to negative c. And we want to know, is it continuous on the interval from negative infinity to infinity? So what we need to do here is to try and simplify x squared minus c squared over x plus c. That'll simplify as x minus c times x plus c over x plus c, which will then simplify to x minus c. Okay? Now if I plug in my x value as negative c, I would get, when x equals negative c, that gives me negative c minus c, which is negative 2c. Now if you look here, if I have 2c, there's not an x for me to plug in. And so, do these two equal each other? Well, I have a negative 2c, and then I have a 2c. Those aren't the same, so is the function continuous? No, it would not be. Okay? So since these two don't equal each other, we have negative 2c and we have 2c. Those aren't the same. Those would not be a continuous function. Now, I will point out, this is the problem that the book has, but that's not the explanation they have. Because then, whenever they go to the explanation, they change the problem. And so I'm going to change the problem for you to show you what the book meant to put. I believe they meant to put a positive c there. And so let's see what would happen if it's at a positive c, or not equal to positive c. We would have x squared minus c squared over x plus c, and that'll factor as x minus c times x plus c over x plus c, which is just x minus c. And so whenever we plug in a c for our x, we end up getting 0. And so are those still the same? No. Okay, because 0 and 2c are not going to be equal. So if you look in the book at that question, they didn't even do it that way. They ended up changing this down here to an x minus c. And so when it factors, you get this. Whoops, that one should cancel with that one. And you end up with x plus c if you factor it. And then if you plug in a c, you get c plus c, so 2c, and these two do match. And so it would be a continuous function. But whenever they made this problem, the question and the description there aren't the same in the book. So if you look at those and you're confused, that's why. They meant to do it where these were plus c's, and this was x minus c. But then they didn't actually do that for the problem. So again, if you look in the book, those are completely different from the question and the solution. They don't match up at all. So hopefully that helps you a little bit with continuity of functions. You do get to omit number 14 on your homework tonight. Make sure to do that so that we can go over everything tomorrow.